Okay, so I'll be talking about, not so much about an idea worth spreading, because particle physics is not so much an idea worth spreading, but rather knowledge worth spreading. And so I will be talking about antimatter this afternoon. And antimatter, if you want to talk about antimatter, you have to go back, like with any good narrative, to the beginning. And the beginning in this case is the moment of the Big Bang, where basically the universe started from one instant to the next. So one moment there's nothing, the next moment there is everything, and basically at that moment all troubles begin. And these troubles begin because what happens at the moment of the Big Bang is that this equation, E is equal to mc squared, takes place. Now what this equation basically tells you is that energy and matter are the same forms of the same thing. You can transform energy into matter, matter into energy. What also happens at that moment is that because of conservation laws, simply charges and so on, what is produced at the moment of the Big Bang is pairs of particles and antiparticles. Matter and antimatter at the same time, always in pairs, and that means that the universe at the moment of the Big Bang consists of 50% of matter and 50% of antimatter. And I've shown you, I can show you here a picture of what happens in such an event, in such a process, where you see these two pink spirals, where one of them is matter, the other one is antimatter. And this happened at the moment of the Big Bang. However, if you look out at the universe nowadays, if you could differentiate between what you see with matter and what you see with antimatter, you would see that the whole universe right now consists only of matter, and that there is no antimatter whatsoever left in the universe from the Big Bang. Although half of it at that moment was made of antimatter, all the antimatter that was there at the moment of the Big Bang has disappeared. So if you think of these processes, this energy transforming into particles and antiparticles, into matter and antimatter, this is not a symmetric process. We thought, one would think that because of conservation of charges, that one has a symmetric universe. In fact, there is an excess of matter that leads to everything we see around us right now, and so the universe is asymmetric. And in order to understand where this asymmetry comes from, one has to understand what differentiates matter from antimatter, or what the particularities of antimatter are. But to understand what antimatter is, one also has to understand what matter is. That is the point where one has to start. And so in the last 50 to 100 years, people have studied matter and have gone further and further down from the macroscopic structures, crystals, down to atoms, down to nuclei, down to the components of these nuclei, protons and neutrons, and to what we consider to be the fundamental building blocks right now, elementary particles such as electrons or quarks. And the only difference between matter and antimatter in this view of the world is that matter is the same as antimatter with opposite charge, or antimatter is the same as matter with the opposite charge. But then if they're identical like this, what about their properties? They should be identical. And this is really the crux of the matter. If we are trying to understand how antimatter could have disappeared at the moment of the Big Bang, we have to look at the properties of antimatter and study these properties. And this is one of the things that is being done at CERN. There are, of course, a number of other experiments that are being carried out at CERN, but two areas of experiments are trying to understand the properties of antimatter, studying antimatter very, very precisely to understand what they're made of and how they differ from normal matter. Now, one of the most sensitive ways of studying antimatter is to measure the properties directly of a particle and of an antiparticle. This has been done for many, many years, and one has looked for small differences up to 1 part in a billion, or 1 part in 10 billion, very small differences. But if one tries to really understand how antimatter could have disappeared at the moment of the Big Bang, one has to be far more precise than that. 1 part in 10 billion is far too imprecise to be able to really discover the difference between matter and antimatter, or any difference that there might be. One has to go to much, much higher precisions than that, and the precision one has to reach is equivalent to taking the Mont Blanc, cutting it off at the base, putting it on a balance, weighing it, putting a little piece of metal, a paper clip, on top of the Mont Blanc, weighing it again and being able to differentiate between the Mont Blanc, the weight of the Mont Blanc, and the weight of the Mont Blanc with a paper clip on top. And to be able to reach precisions of that, at that level, one has to use systems that are not sensitive to any other systems around them, not to electric fields, not to magnetic fields, not to the Earth's magnetic field, not to experimenters walking by, and these are neutral systems. Luckily for us, antiparticles will behave just like particles, at least to very, very high precision, and can form atoms. They can form atoms just like a proton and an electron can form an atom of matter. An antiproton and an anti-electron can form atoms of antimatter. And if one measures the light emitted by these anti-atoms, which is basically the same light as the light emitted by normal atoms, one can measure this extremely precisely to the level of precision that we're trying to achieve here. So in 1996, there was an experiment started, several experiments, who tried to make antihydrogen atoms. This is what the experiment looks like. It's basically a mess of cables. It's a small experiment, university-style experiment. If you've seen some of the large experiments at CERN, those are building-sized experiments. This is a very small, compact experiment. But the goal of this experiment is basically to make antihydrogen, to make atoms for the first time. They had never been made before, because if you want an atom of normal matter, you just dig it out of the ground or you pull it out of the air. If you want to make atoms, you have to find out a new way of making atoms. So this was the first step. But this is only the first step, because once you have the atom, you want to study it, and you want to see the light emitted by it. And for that, you have to trap it. You have to close it inside a cage. You have to cool it down to very, very low temperatures, because any movement of this atom will change the color of the light that it emits. And you want to measure the light emitted by this atom. The first step was started in 1996 and was completed in 2003, 2004. So this took something between 5 and 8 years, trying to do something that had never been done before, something completely new. The second step, trapping antihydrogen, started about 3 years ago and has not been successful yet. Although people have been trying for several years, you can expect that a technological leap into this next technology to be able to trap antihydrogen will take another 5 years until it's successful. And once you've achieved that, you have to take the next step, which is to cool down antihydrogen to temperatures which are about 1/millionth of a degree above absolute zero. Almost complete standstill that are not moving at more than 1 millimeter per second. So the point that I'm trying to make here is that until we get to the point where we can measure the light emitted by antihydrogen, by anti-atoms, it will take a very, very long time. A decade, perhaps 2 decades. Now, there are 2 things you can do in a situation like this. If you have a long-term goal, first of all, you can keep picking at the object, and you can keep trying to develop new technologies, and you can keep trying to improve your current understanding of technologies. And then 5 years down the road, you solve the next problem. 10 years down the road, you solve the problem after that. And then 20 years down the road, you discover that somebody else has already done it much better than you could ever do it 10 years before. Which is exactly what has happened in the case of antihydrogen, because another experiment, in a certain way, in an analogous way, has already compared the properties of particles and antiparticles to the precision that they're trying to achieve here. So in such a case, either you keep on working in the same direction, or you take a step back and you rethink the questions that you're trying to answer. Is this the best process? Is this the best approach? Is this the best way forward to be able to look for a difference between antimatter and matter? And I would argue that in some cases a detour may, although in principle take longer for the well-being, end up being shorter and more scenic as well. And so the question that the detour that we're talking about here is the measurement of the gravitational interaction of antimatter, the fall of antimatter. The question I'm asking is, if I take an apple and I let it fall, and I take an anti-apple and I let it fall, what will they do? The apple will fall like a lead brick, but what will the anti-apple do? And by measuring something like this, we might learn something about antimatter that distinguishes it from normal matter. So it's basically a reproduction of the experiment that Galilei supposedly carried out on the Tower of Pisa by taking a ball of lead and a ball of wood and letting them fall at the same time. Now, to do this requires a number of steps, but the important element in this is that it is a different way of looking at the same question as before. And not only is it a different way of looking at the difference between matter and antimatter, but there's also a link to cosmology. Because if one looks at where there are difficulties right now in cosmology, and in global picture and global understanding of the universe, gravity comes into it in a very, very strong manner. There are indications at a certain number of points that gravity just doesn't behave like we think it does, and there's presently no way to bring gravity into particle physics. So this might open up a breach, a very small breach, for bringing in gravity together with all the other forces. The experiment itself is a little bit complex or simple, depending on how one looks at it, but it's based on two very simple ideas. One of them is that you should steal and borrow and beg wherever you can. So rather than staying within a small context of only high-energy physics, one tries to bring in ideas from many different areas: atomic physics, laser physics, very cold temperature physics, plasma physics, atom interferometry. Technological advances that have taken place in many different fields are brought together into one single experiment. And the other idea is simply to use a different approach, a different viewpoint, rather than trying to trap an atom and try to fight the problems that one has to fight to be able to trap them. Use the defaults, the problems that the other experiments are facing as a benefit, as an advantage, in order to be able to carry out a measurement. So the real bottom line of this is that it requires going outside of the normal area of expertise and the area of knowledge that is available to particle physics in general by contacting these other groups, these groups outside of high-energy physics, by bringing in universities, technologists, people with expertise in areas that are not usually part of high-energy physics. Contrary to normal high-energy physics experiments, which usually take a decade or two to run, this experiment is a very small experiment. It will run in about a few years, and so you can expect a result in a few years' time, in 5 years at the latest, on whether apples fall down, anti-apples fall up, and gravity has a component of levity. And with that, I have finished my presentation.